Hello 20-1 students. So today we're looking at absolute value equations. So moving on from functions to, again, just like a step more complicated. So to start out today, we're going to do a little bit of an investigation again. So if you want, you can pause the video, try and work yourself through this, and then watch back and see if you get kind of the same ideas out of it as I do. So in the beginning here, it says consider the absolute value equation. Absolute value of x is equal to 5. Use the number line to geometrically solve the equation. How many solutions are there? So basically what we're saying is the absolute value of some value on this number line is equal to x. So if we think about, obviously the absolute value of 5 is 5. Are there any other possibilities of an absolute value that would equal 5 on this number line? So we can cross off like 5 would be there. Well, negative 5 as an absolute value is equal to 5 as well. So we see that there's two solutions for each of for the absolute value of x is being equal to 5. Then it asks us how many solutions are there for the equation absolute value of x equals 10. So again, we would have the same thing, right? Absolute value of x could be negative 10 or positive 10. And same thing for absolute value of x. We could have negative 15 or positive 15. So basically, to generalize this, we can say that for the absolute value of x being equal to b, as long as b is not equal to 0, there's always going to be two solutions, because it could be negative b is equal to b or b is equal to b, right? So there's two possibilities as long as there's a positive and a negative version. So then they ask us to make a conjecture about the number of solutions that would exist for an absolute value equation. So as we've seen, for any value where we have a positive and a negative value, there would be two solutions, right? So if we have a positive, negative value, we'd have two solutions. What about if we think about in the previous example, they did mention b cannot equal 0. What if we had absolute value of 0? How many possible solutions are there? Well, 0 has no positives and negatives, so there's only one possible solution for that. So the other thing we could say that if we have an absolute value of 0, there's only going to be one solution. Okay. So, and then it says solve the absolute value of equation, absolute value of x is equal to 0, and we know that that would have to be set up like that. Lastly, it says, is it possible to have an absolute value equation that has no solutions? So if we think about it, what is the only possibility for an absolute value that is not a solution? Well, like we learned, for absolute values, we have to have a positive value, right? So we could say like absolute value of x is equal to a. The only thing that would not be possible is the absolute value of x to be equal to negative a. If we had an equation like this, then we would say that there is no solution. What does that mean in terms of a graph? Well, when we're graphing these absolute equations, the solution is always the point of intersection between the two components of the piecewise function. So if you remember, we learned about how you'd have like we would say y is equal to x or negative x. Those are our two components of the absolute value equation. So when we've found solutions before, like in a graph that has two solutions, for example, the solutions for these are the points where these two graphs intersect. Now, if we have a negative value, remember that that's not going to be possible to have an intersection with an absolute value, because we can't have a negative value for y in that absolute value graph, and so then there would be no solution. Okay. I don't know if that made tons of sense, but we're going to do an example where you'll see it, so hopefully it'll make more sense when you actually see the example of it. All right, so what is an absolute value equation and how is it different from an absolute value function? Well, an absolute value equation is one that includes the absolute value of an expression involving a variable. So basically, like up until now, we just had like y is equal to the absolute value of 6 minus x, for example. Now we actually have an equation where the absolute value of 6 minus x is equal to a numerical value, and we have to solve it basically. So there's two cases to consider to start with, which is that the expression inside the absolute value symbol is positive or 0, or that the expression inside of it is negative. So we'll look at, in all of our equations that we look at, we need to consider those two cases. Okay, so when we're asked to solve the absolute value of 6 minus x is equal to 2, the first thing we need to do is figure out what the two possible cases are. So our first step is to determine the piecewise functions. So the first possibility of the absolute value is that we just have 6 minus x. The second possibility is that we have the negative value of that, so negative 6 minus x, which then of course is equal to, you just multiply the negative by everything inside the bracket. So negative times by negative x becomes positive x, and negative times positive 6 becomes negative 6. So I usually, when I multiply that out, I usually rearrange it so that I don't have like negative 6 plus x. I just have x minus 6. Just seems like a little bit more simple. Once we have our piecewise functions, we need to determine what the acceptable values of x would be for each. So this is kind of like in previous chapters where we had to determine the non-permissible values. So we're basically determining what could be the domain of x, essentially. So in the first one, and we want to do that for each case here. So for case number 1, 6 minus x has to be greater than or equal to 0. So if you remember in the last lesson, I mentioned that for your original graph, you're always going to have greater than or equal to. For your absolute value version, it's always just going to be greater than. Okay, so for 6 minus x is greater than or equal to 0, if we rearrange that to solve for x, we can add x to both sides. So that cancels out here, and we're left with 6 is greater than or equal to x. Okay, so that's basically like our domain for the first case. For the second case, we had x minus 6 has to be greater than 0. And so again, if we rearrange this, we would have to add 6 to both sides. Oops, add 6. And so we're left with x is greater than 0 plus 6, which is 6. Okay, so now we have the acceptable range of values for each case of the equation. Then we need to solve the equation, basically, and determine the values of x. So we're solving for x, and then once we've solved for x, we want to determine if those solutions match what we've determined in step 2 here in terms of what the acceptable values are. So for this first one, 6 minus x is equal to 2. So let's see, we could add, let's say we'll add x to both sides. So 6 is equal to 2 plus x. And then we want to isolate the x here, so let's subtract 2 off of both sides. So that's going to eliminate it here, and 6 minus 2 is 4. Whoops. Not 4 is equal to 4. 4 is equal to x. So we have one possible solution for x. We want to look back at our acceptable value for this case. In this case, x has to be less than or equal to 6. And so one way that you can always solve this is just to say like 6 is less than or equal to, oops, I don't know why I keep doing that. 6 is less than or equal to x. And if we sub in our x value, 6 is greater than or equal to x. 6 is greater than or equal to 4. Is this statement true? Yes. So that means that this is an acceptable value for x. For case number 2, if we want to solve it, so we're working with the modified version. Remember, there's that negative value there. So the modified version is x minus 6. So for case number, that was number 1. For case number 2, we would say x minus 6 is equal to 2. And so then we would just do, if we want to isolate x, we want to add 6 to both sides, which gives us x being equal to positive 8. So that's our solution, and then we want to see if it fits with our acceptable range. So x is greater than 6. In this case, x is 8. And 8 is greater than 6. That's a true statement. So then we know that this is also an acceptable solution. So we have 2 acceptable solutions, which means that the 2 components of our graph are going to intersect at 2 points. Now with this, we just want to verify our solution by graphing. So essentially, if you want to use your graphing calculator to solve for this, remember you're going to go into your absolute value. So you go to Math, Number, and then choose absolute value. And essentially what you want to do is add in each part of the graph separately. So in this case, we have 6 minus x on one side. 6 minus x. So that's going to be our y1 graph. And then we actually just make the other side into our y2 graph. So we're just saying y2 is equal to 2. Now if we go to our graph, we see that, sorry, it's kind of in a bad spot for reflecting there. There we go, that's better. So we can see that we have 2 intersection points on the graph. If you need to, like if you're not certain about the intersection points, you can go second function trace, and you can go to intersect, and then you could go, it's going to ask you first curve. So you just want to make sure you're kind of close on one of the graphs to the intersection point you're interested in. So scroll over to that, hit enter, and then you'll see that the second star kind of jumps up and asks you second curve. We're already pretty close to the intersection, so I'm not going to move it much more. So you just hit enter, and then it'll say guess. So you hit enter again. And then it says intersection is at x equals 4, y equals 2. And so we can see that our solution x equals 4 is valid. Okay, you can do the same thing for the other side. You would just go in, second function trace, intersect, but this time you just want to make sure that you're closer to that intersection. So you'd hit enter, 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 and we see that our intersection is at x equals 8, y equals 2, which was our other solution. So that is verified. Okay, so you can check it by graphing. If you look on the filled in notes, you'll see that I actually sketched out the graph really quickly. So just be sure that if you were in a test situation and you were asked to verify with graphing, that you know how to kind of quickly draw that out as well. And then maybe just make a statement like I did in the filled in notes, which is that when y equals the absolute value of 6 minus x, x is equal to 4 and 8 when y equals 2. Okay, so that just kind of confirms basically that the intersection points were correct. All right, so you might want to pause the video a second and try an example that's similar to the one we just tried. So see if you can solve this one and come up with the proper solution using the method we just did. And again, you can check the filled in notes for the full worked solution to that. So if you don't get, like if you do all the work and then you put it into your calculator to graph it and you don't find the same answer, then go and check those filled in notes to see where you went wrong. All right, so our next type of question is a word problem. So solving an absolute value problem. We have a computerized process controlling the amount of fish that is packaged in a specific size of can. The computer program sets the ideal mass at 170 grams, but allows a tolerance of plus or minus 6 grams. Solve an absolute value equation for the maximum and minimum mass, which is the variable m, of fish in this size of can. So the first thing you want to do with a word problem is basically figure out what is the equation. So in this case, what you want to be aware of is how absolute value equations are set up with relation to the numbers that they're representing. So in an absolute value equation, we have like x minus b is equal to c. Now, b is always representing the midpoint. So if you think about those questions we did with a number line, I think it was in the last lesson, if you were looking for the distance on either side of the number line, then you would do x minus the middle in between them. So sometimes that's 0 or sometimes it's another number. And then the c value is the difference from the midpoint. So like if we had, I'll just pull back this number line here. So say if we had 2 was our midpoint, and then we had 0 and 4 were our difference, we're 2 units away from our midpoint. So our equation for this one would be, for absolute value, would be x minus b is our midpoint, which was 2 in this case, is equal to, and then c is your difference from the midpoint. In this case, I actually did that the same, so that's maybe not the very best example. But yeah, so this would be your equation for that, okay? So with this one, c is the difference from midpoint. Difference from mid. Okay, so if we think about what's going on here with this can of fish, it's basically that the ideal mass is 170, but there can be a difference of 6 extra grams or 6 less grams, right? So if we think about that, it'd be like 170 is the ideal, which is basically going to be the midpoint, but we could go up to 6 units higher, which would be 176, or we could go down by 6 units, which would be 164. Okay, so this is, if we think about what's happening here, our midpoint is 170, and our difference on either side of that is 6 units. So that would make our equation x minus the midpoint of 170 is equal to the difference from the midpoint, which was 6 units. Okay, so this is our equation for this particular word problem. Once we have our equation, all the steps are the same as the question that we just did. So the first thing we want to do is determine the piecewise functions. So for number 1, it's just going to be x minus 170. For case 2, it's going to be the negative of x minus 170. So that's basically going to be negative times by negative is positive 170 minus x. Okay, so these are our 2 possibilities. Then we want to determine our acceptable values. So in this case, it would be x minus 170 is our original, right? That's inside of our absolute values. So that means it needs to be greater than or equal to 0. So we could say x has to be greater than or equal to, if we rearrange this algebraically, we're adding 170 to both sides. So it has to be greater than or equal to 170. For case number 2, 170 minus x has to be greater than 0, right? So this is our second version, so it's just greater than 0. And so if we rearrange, we add x to both sides, we end up with 170 is greater than x. Okay, so those are our acceptable ranges of values for x. Now we just want to solve for x. So x minus 170 equals 6. So we want to add 170 to both sides to isolate the x. So we end up with x is equal to 176. We want to check if that matches with our idea here. Is 176 greater than or equal to 170? Yes, 176 greater than or equal to 170 is true. So that means that this is an acceptable value for x, or an acceptable solution, I guess is the proper way to say that. So that was for case number 1. For case number 2, we have 170 minus x, so let's use the one that we already did there. 170 minus x has to be equal to 6. So if we want to rearrange, again, I don't like to end up with the negative, so I'm going to add it to that side. So it's going to be 170 is equal to negative x plus x is 0, 6 plus x. And now I can get rid of this 6 from both sides. So we end up with 170 minus 6 is 164. Which is equal to x. And again, we want to confirm if that fits our acceptable range. So 170 is greater than 164. Is that a true statement? Yes, it is. So that means that's another acceptable version of x, or value for x. And that makes sense because that's what we came up with on the number line, right? Last of all, we would just want to graph that really quickly and confirm that those were proper intersection points. So we go to y equals, and it is x minus 170, and it has to intersect with 6. So if we go to our graph for this one, we're actually going to see not much happening, right? So we see this going on here. Now, what did we say? We said that we would have x values for 164. So all this is telling us with our solutions is that we would have x being equal to 164 and y would be equal to 6, and x would be equal to 176 and y would be equal to 6. So we need to change our window for that. So let's make our x maximum. We don't really need this minimum here. Let's maybe make that. Let's see what that does. There you go. So now you can see your two intersection points. So just keep in mind when you're setting up your graph, just keep in mind to set the window appropriately for where you're looking at. So if your x values are high, you just need to go into your window and change that. I don't know, I could even, like this is pretty, and this could be like 0, makes it a little bit more zoomed in there. And then again, you can go in and trace your intersections. So go to intersect. Sure, let's do that one first. And it says 176 and 6, right? And you can do it for the other side and check that solution as well. So we can see that our solution was correct by doing that. All right. One more example here, and then we'll wrap it up for today. So this is looking at absolute value equations that do not have a solution. So the same, now even though in this case you're told there's no solution, you still approach it the same way. And of course on a test you won't be told that it's not going to have a solution. So basically with any one of these equations you approach them the same way. So first of all, we want to determine our piecewise functions. So when you have an equation like this where you have the absolute value and another value here, don't worry about this when you're determining your piecewise functions. Piecewise functions are always only looking at the component inside the absolute value brackets. So basically we have 3x minus 4 is going to be our piecewise function. And well, I might combine these first two steps of finding the appropriate value. So this is our original one, so it has to be greater than or equal to 0. So 3x has to be greater than or equal to 4. If we add 4 to both sides, then we need to divide out that 3. So it's going to be x is greater than or equal to 4/3. Okay, so there's our acceptable range for case number 1. For case number 2, we're going to have the inverse of this, so it's going to be negative 3x minus 4, which is going to be negative times by negative gives us positive 4 minus 3x. And as this is the second component, it has to be greater than 0. So again, we can solve this. So add 3x to both sides, and we get 4 is greater than 3x. Again, we need to divide out that 3 from both sides, so we end up with 4/3 is greater than x. Okay. So those are our two acceptable values. Now we want to try and solve for x. Okay. So solving for x, we're going to have 3x minus 4 plus 12 is equal to 9. Then combine the like terms. So negative 4 plus 12 is plus 8. So 3x plus 8 equals 9. And then we want to start isolating our x. So we want to subtract 8 from both sides, which means we're going to have 3x equals 9 minus 8 is 1. So x is going to be equal to, we need to divide the 3 out of both sides. So that's going to give us a 1/3. Now if we compare this to our value, x is 1/3 according to this solution. And according to our statement, that has to be greater than or equal to 4/3. Is this statement true? Is 1/3 greater than or equal to 4/3? It's false. So that means that this is an extraneous solution. Extraneous solution. Just like we've looked at before. Okay, doesn't fit with the non-permissible or acceptable values. So for case number 2, we have 4 minus 3x plus 12 equals 9. Again, combine your like values. So 4 plus 12 is 16. And then, so just combining those two numerical values, minus 3x equals 9. So just keep in mind that you have to keep that negative together with the value. Then we want to move this over to the other side, so that means we would need to subtract 16 from both sides, which gives us negative 3x is equal to 9 minus 6. Oh, whoops, minus 16 is equal to negative 7. And then x is going to be equal to negative 7 over negative 3. And of course the negatives cancel out, so we would say x equals 7 over 3. Then we want to compare it to our value. So x is 7 over 3, and that has to be less than 4/3. So is this statement true? It's not, it's false. So that is also an extraneous solution. So then we would say in our final statement for this, there is no solution. And what that looks like when we graph it, so again, you can always check these ones as well to see if it makes sense. So if we plug in 3x minus 4, and then, oops, delete that out, plus 12. Okay, so don't forget that extra part there, and it has to be equal to 9. I'm just going to go here and make sure that I'm at standard again and go to my graph. Oh, this might be a little bit too short. Yeah, I'm going to make my window just a little bit bigger in the Y scale. So Y max, let's make it 20. There we go. And so this is what we mean when there's no solution, is basically that those two parts of the equation do not intersect with each other, right? So here we have the left side of the equation, and it never touches that y equals 9 component. So that's what we mean when we say there's no solution. Okay. All right, that's everything for absolute value equations for today. So I've divided that section into 2 parts. So in the next lesson, we'll look at some different versions of these absolute value equations. But for today, you can just work on the practice problems that I've assigned from the textbook, and I will see you in the next lesson when we cover the second component of this.